I'll change it afterwards if need be.
The idea was to kind of reset and let people, it's now September, it's time to learn, and let's start back to basics kind of and get people up to speed.
All right, so we're set up on YouTube. Hi, everybody who's joining us, and the usual, you're probably sick of hearing me say this, but just in case, if you're on Zoom, don't forget to change your little chat bar to all panelists and attendees from all panelists so that everybody can see you and talk to you. So welcome, everyone. We are back. Chris and I had a chat, and we're going to keep running with Insider's Guide until at least the end of October. And then we're going to reevaluate again and see if we can get some more stuff going. There's some big changes at Rask National coming up at the end of the year, and so we may end up being a little bit busy. So we'll see what happens. Teaser for those of you who are Rask members, there's going to be some changes, and it's going to be really interesting. But for today,
good things.
Very exciting things.
Don't get people worried.
Don't worry, it's all good stuff. It's super exciting. We're really excited for it. But today we figured we would take the opportunity, because it is the beginning of the school year again, and it's a bit of a reset moment, to go over some of the basics that we haven't necessarily touched on in the series before. There's going to be some that are repeats, but we've had a lot of questions about things like our right ascension and declination and how the sky moves and stuff like that we may not have covered as in depth. So we're going to talk about that stuff. And we have our next sessions planned out as well, which are on the website now. The biggest, most important ones, let's see, I'll send out the link to the rest of the sessions. But for now, we're going to cover some of those basics, and then we're going to cover some fall targets as well as we get into fall observing. There's the link for the rest of the sessions. And Chris.
All right, let me share my screen here. I love using Stellarium. I know, we talk about it a lot, but it's such a powerful tool, and it's an excellent thing to sit down and learn how things work in the sky, because you can just experiment with it so nicely. So I recommend, if people want to learn how to install it and get going on it, you can go back to our first session, which was the Intro to Stellarium, and watch that and get up to speed. But I'm gonna demonstrate much of what I talk about today using Stellarium. And the first thing I wanted to do is talk about sky motions. So what's going on? So we all know that things rise in the east and they set in the west. And if you live in the northern hemisphere, that means things rise, things move kind of left to right. If you live in the southern hemisphere, as we did a couple of weeks ago with our southern hemisphere tour, it goes the other way. So it's a little bit strange, but if you grow up there, you're used to it. And the Earth revolves. The reason that things cross the sky, like the sun, and I can sit here and use the keys here to make things move back and forth. So the sun is moving across the sky because the Earth is revolving. The Earth is spinning on its axis. It does one complete rotation in about 24 hours. And so that's 360 degrees of motion in 24 hours. And it does that day after day after day after day. And if you do the math, it works out that things move across the sky about 1 degree every 4 minutes. And at 1 degree is about the width of your finger. We'll get into a bit more of that. And so if you're using a telescope on an object and you point your telescope and the telescope doesn't have a motor on it, and you center the object, within a couple of minutes, it's gone because of the Earth rotation. And that causes everything to revolve around the sky. And if we just go into the evening sky here, so the sun does that, and then all the planets and stars and constellations, they all move relentlessly and steadily across the sky because of the Earth's rotation. If you see anything moving faster than that, then it's either man-made, like a plane or a satellite or something like that, or it could be a meteor, or in rare cases, it could be a comet, because comets actually do move faster than the stars, and depending on its direction it's going, it could be, moving slightly faster. But generally speaking, everything's got that steady pace to it. So given that 4 minutes a degree thing, that means that if you're watching the sunrise or the moonrise, or the sun and moon rise and set, it takes them 2 minutes for the disk of the sun or the disk of the moon to fully clear the horizon or drop below the horizon, because they're approximately half a degree. So that's half of 4 minutes. Right. Now, the rising and setting isn't exactly east to west, and that has to do with the Earth's tilt of its axis. So we'll cover that a little bit more in a few minutes. Now, in astronomy, the best time to look at an object the most clearly is when it's highest in the sky, and that's because we're seeing it through the least amount of air. The Earth's atmosphere acts as a detriment to the light that's traveling to us from the distant objects. So the higher you look in the sky, the thinner the layer of air you're looking through. And so we always like to look for objects when they're highest, and that's good for planets, it's good for galaxies and nebulas and star clusters and things like that. The moon is not so important because it's sort of big and easy anyway, but so there's a line that you can connect from the North Pole to the South Pole, and it's called the meridian. So I'm just going to draw that line. So it'll start in the south, it'll go over your head. So Z is the zenith, that's straight overhead, and set behind you in the north. And so objects, they rise in the east, they go higher and higher and higher, and then they set in the west. And I can use something like, if you watch Vega here, so I can have, well, let's see, I'm just gonna hide the daylight for a second here. So a star will rise. Let's use Altair. So Altair kind of rises in the east at around, let's see, around 3:20 p.m. and hour after hour, it crosses the sky. Now, if I make the horizon flat, you can see that rise and fall. So I'll just do that again. So there it is down here in the east. It's gonna go east to west, and it's gonna be highest around, for Altair, it's gonna be highest around 9, almost 10 p.m. So we call that crossing the meridian or transiting. That's two different words that we use for it in astronomy. And after it reaches this point, it's going to be sinking lower. And so if you're watching something rising in the evening and you get up and stay up late, you can watch it then sink down lower on the other side. So that's how the meridian works. And that's true for anything that rises and sets in the sky. All right. Now, meanwhile, on top of that, we have the Earth orbiting the sun, right? And the Earth is orbiting the sun once per year, and that's 360 degrees. So if you do the math, it's about, I think it's about 15 degrees per, I forget what it is, but anyway, it actually ends up causing the stars to rise 4 minutes earlier each night. So forget about the Earth rotation. We're just talking about how the sky evolves night after night after night. So if you go out on the same time every night and look at the sky over a number of days and weeks, you're going to notice that things are moving from where they were when you started your observation. And so that motion, much like the Earth's rotation causes things to go east to west, also causes objects in the sky to migrate from east to west. And it works out again that it's about 4 minute different per night. And so that if you do the math, that's about half an hour per week, right? 28 minutes, about half an hour a week. So if you're waiting for something to come into view, say a constellation or a planet, every week that goes by, it's going to rise a half an hour earlier. So we've all been waiting for Mars to come into view. And as the weeks tick by, it's rising earlier and earlier and earlier. So things start rising, in the pre-dawn, and then at some point they're rising around midnight, and then a month later they're rising in the late evening and so on. So you can sort of time things that way. And the effect of all that is that the constellations themselves, they migrate across the sky. And as they migrate to the west, they're actually traveling towards the sunset, if you're talking about evening. So let's just bring the sun back here. So we've got the sun sitting here in the west. And it means the constellations are kind of being swallowed into the drain of the sun's light. And so that's when we start losing sight of them, is when they get too close to the sun and they're overcome, they disappear in the glow of the sky. And so that causes us to get new sets of constellations in each season. And really it's almost, you know, every few weeks we've got sort of another constellation peaking up at a reasonable time over the eastern horizon. So the summer triangle constellation that we've talked about, you've heard Jen and I talk about the summer triangle a lot. So let's just bring this up. So that's Deneb, Altair, and Vega. And this is the sky on September 8th. A month from now, you see how it's hopped to the west, all right? And that would be the equivalent of 30 days times 4 minutes or a couple of hours of travel. And then and so on.
Can I add in an extra thing that makes it even more complicated, but I think is worth noting?
Go ahead.
Because the days are also getting shorter, it's not relative to the sunrise, it's relative to that time of night, or sorry, sunset. So even though sunset right now is at like 8:30, this, you know, at this point in the year, and this is in December, sunset will be at 5. And so this will actually be 4 hours after sunset. So if you're just going out after sunset to look at the stars, you may not see this motion as much, especially at the end of the summer as the days get longer. Yeah. It's kind of accelerated in the opposite direction in the springtime as the days get longer, as far as I know. But as you're going into the fall and winter, you actually get a really long time to see the summer triangle because of that sort of like the sunset keeps being earlier in the night.
Yeah, so the summer triangle kind of introduces summer. When the summer triangle appears, the summer season has arrived, summer stargazing season has arrived, but it's visible until January.
Yeah.
Just because as it's getting into that drain, that drain I said about the sunlight, that sunlight is also being overwhelmed by the earlier sunsets, and so it gets dark earlier.
We also have a quick question, which is, does rising, when you say rising, refer to when it becomes visible, or does it refer to its movement over time? Like, is it rising until it gets to the meridian and then setting after that? Or do you mean just rising as it's coming up above the horizon?
So most of the time when astronomers refer to something rising, they're talking about the moment that it appears above the horizon. It's when it's lowest in the sky. So when I'm talking about, if I want to look at Mars, here's tonight. If I advance the time till around, yeah, so there's Mars. So Mars actually rises or clears the horizon at about 9:15 or 9:20 p.m. right now. But you can see that's going to change for two different reasons. It's going to change because of the way Earth's orbiting the sun and that 4-minute difference, but also because Mars itself is moving. And that complicated. So here's a fun fact. So there are lots of times Mars's speed of motion is actually often about equal and opposite to the Earth's to the drift of the stars. And so you can get times where Mars rises at exactly the same time for week after week after week after week, because it's moving 4 minutes worth, but the sky is moving 4 minutes worth the other way due to Earth's motion.
That's so cool.
There was a period last year where I was writing my skylights about when Mars would rise, and every week would be within a minute of what it was before, just because it's kind of swimming upstream while the sky is rotating.
That's so cool.
Huh. Yeah. Let's talk about. I don't want to go super in depth into the seasons and things like that, but we could talk about the ecliptic a little bit and the celestial equator and things like that, if you wanted to say a few words about that, Jenna.
Yes, so we had a question from a viewer over the weekend who was asking about how come, and there's another question in the comments here, the difference between ecliptic and equatorial. The question from the weekend was about how come the ecliptic is the path that the sun travels along, but the sun seems to move all the time and the ecliptic is supposed to be staying the same. And this is not an easy question. It's also kind of counterintuitive. Do you mind, Chris, if I bring up my stellarium? Is that okay?
Yeah, I'll stop this for a second.
I mean, they're more or less the same, but then I get to press all the buttons. So the ecliptic is the line that the sun passes along, but it's essentially, I like to refer to it as the plane of the solar system. So if you've got a hula hoop and you hold it up to eye level, that line that the hula hoop is blocking out is the plane of the solar system, and it would be the ecliptic. And the ecliptic stays the same all the time, but we are not level with the ecliptic. It would be like having the ecliptic up 23.5 degrees or slightly off. So we are tilted, and because we're tilted, the sun does seem to move location in the sky as to where it rises and sets. And so I believe equatorial, I mean like the equator of, hold on, let me bring up the,
Yeah, show the equator.
here's the equatorial mounts, and then like the middle, essentially the line over the equator on Earth is here. That's the center of, that's like the line that runs east to west. That's the center of our celestial sphere. Whoa, sorry. It's the center of our celestial sphere. The ecliptic, there we go, is not over that line. The ecliptic is off slightly.
Yeah, they're like two hula hoops, but 23.5 degrees off from each other.
Right. And so
Yeah.
if the ecliptic were directly over the equator, and that is to say, if the Earth was not tilted at all, if the Earth was like perfectly in line with the rest of the solar system, all of our days would be the exact same length. Everything would be, the sun would always rise in the same spot. It would be like the equinox every day. We would never have that tilt. We would never have winter. We would never have summer. We would just have life.
Yeah.
It would just be one season.
That's what Jupiter has. Jupiter's like that.
Oh, I guess is Jupiter interesting? Okay, so that's
it has
cool.
almost less than 1 degree tilt on its axis.
Cool. So Jupiter doesn't have seasons. Yeah. So we are tilted so that and I'll show you this I'm going to bring up the date and time and move the date and time around little by little. So here's what happens during the day. The sun does not. Let me zoom in a little bit. The sun, it doesn't look like it's following the ecliptic, but that's because the ecliptic is staying in the same spot as the sky turns around it. You can see this better with the stars. So see how that's Jupiter right there, right on the ecliptic, and it stays in the same spot. It just looks like the ecliptic is wobbling. Now this is kind of cool because in the summertime, let's go back to June. As you all know, the sun gets really, really high in the sky, as shown here. But at night, when you're observing in the summertime, the planets are really low in the sky. They're right down close to the horizon. And that's because of that tilt. You kind of have to have, and Chris described it as a teeter-totter. You kind of have to have one or the other. So either the sun's really high in the sky and the planets are all really low in the sky, like what happens in the summer, or in the winter, we're facing a different direction and it flops over, and the sun's really low in the sky and the planets are really high in the sky. On the equinoxes, when the equator, the sun is, where the lines cross and where the sun is directly over the equator, then you have the sun at the same height in the sky as the planets at night. It's that wobbly middle point, perfectly balanced.
So what's cool is that because full moons are always opposite the sun, right?
Mm-hmm.
So the full moons in December are really high in the sky, just as the sun is really high in the sky in June.
Yeah.
Yeah. So if you look out onto your yard, into your backyard on a full moonlit night, like at around midnight or a little after, the shadows that are being created by the full moon would be the same shadows created by the sun at noon in the summertime.
That's a really cool way of picturing it.
Yeah, it's just swapping the illuminators around.
Yeah, super, super cool. Maybe, I don't know if we can do that just by switching this to 12, probably not.
Well, let's move on.
Anyway,
we can always come back if somebody wants to elaborate. All right, let's see. All right. Yeah, we often spend like a whole class lesson on just some of these topics. So
it's also, I mean, it's hard stuff to visualize, right? You don't it's not stuff you think about all that often, and then you're only looking at it from your one perspective, which is here on Earth. So exactly. it can be hard to picture it in other ways.
All right, so the next topic I had under my list was sources of light in the sky. So only stars emit light, are the only natural sources of light, right? And aside from the sun, all the solar system objects that we're used to seeing, all the planets, the asteroids, the comets, everything else, they're all shining by light, reflected sunlight in the visible spectrum. You can get objects that are actually glowing by their own infrared radiation, or by their radio emissions that they've produced by the electromagnetic behavior in their interiors. But as far as what we see in the sky, everything we see in the sky is reflected sunlight. Right? Now, the stars are shining because they have nuclear fusion occurring in their cores, primarily hydrogen being fused into helium, which is an energy positive reaction that produces energy. Those energetic photons from those reactions, the sun is so dense inside, it can take 170,000 years for that light to escape the core of the sun to the sun's surface. And then from there, it has a much shorter time to travel to us, to Earth. And that's because inside the sun, the photon can't travel at the speed of light, or if it does, it's going to bump into something and have to reverse and wind and sort of do this random sort of breakout that it eventually takes a long time to break out. Now, when next time you're out on a starlit night, and we've talked about this before, notice that the stars have different tints or different colors to them. And that's because they're actually shining they have a different surface temperature. And the general rule of thumb is that if a star is cooler, it's reddish. And if a star is hot, it's white or maybe blue-white. So when you look at a bright star like Vega, Deneb, Altair, and the Summer Triangle, those are hot, bright white stars. And if you look at a star like Antares or Aldebaran or some of the other cool red stars, then they're much less energetic. They're much lower in temperature. And our sun, being a yellow star, it's in the middle of the range. So it has a surface temperature of about 6,000 degrees Kelvin. What that means is and I don't want to get into a lot of stellar evolution in this particular session today, but the stars that are burning so hot are burning their fuel faster. So their lifespans are very short. So a star like Vega might only live for millions of years, whereas our sun is going to live for 10 billion years because it's burning its fuel with the thermostat turned down much lower. So the Vega's got its pedal to the metal and it's burning all its gas, and our sun is just sort of in the Prius doing its thing, gently, slowly. So you can notice the different tints of the star colors if you look for them. And we've covered them in previous sessions. And I'm going to, towards the end of the session, I'll mention some things to look for on the autumn sky. The other thing to bear in mind is that the stars don't all shine at the same intensity. So a star can be a big star or a small star, and it can also be more energetic or less energetic. And so two stars that look the same brightness in the sky, one can be pumping out much more light, so it could be actually much farther away, but look just as bright as the one that's close to us. And so the range can range from a fraction of the amount the sun puts out to many thousands of times brighter than the sun. And there's an object I'm going to mention at the end of the session that puts out many thousands of times more light than the sun does. And it's a really cool object. All right, so these are just sort of general astronomy basics that we want people to sort of appreciate. So when you see an object from the solar system in the sky, you're actually seeing it by the light, the sun's light that has traveled out to the planet or the asteroid or whatever, reflected off its surface and then come back to your eyes. And so there's a sort of a time that it takes for things to travel. Now the light travels at the speed of light. That's the famous speed of light. It's about 1 million kilometers per hour. So 1 million kilometers per hour, or 2.99 blah, 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 blah kilometers per second is the speed of light, right?
Meters per second. Yeah. 2.9 times 10 to the 8 or something.
And so all the light that's in the universe is all following the cosmic speed limit, and it takes its time to get from A to B. So anything that we see in the sky has left its source and it's arrived on Earth to your eyes, and it's taken a certain amount of time to get to you. Now, if something is close to you, that time can be very brief. And if something's really far away, that can be a long, long time. So the moon, when you see the moon, it's lit up by the sun. The light, when it reflects off the moon, it takes about 1.3 seconds to get to Earth. So we're seeing the moon 1.3 seconds ago when we look at it, right? So this gets into the time travel aspect of astronomy
Yeah.
and mission stuff. The sun's light takes 8.32 minutes to get to Earth. And that's also true for the sun's gravity, right? So people do the thought experiment where what would happen if the sun were plucked out of our solar system?
Yes.
And we wouldn't know for 8.32 minutes. We wouldn't know, we wouldn't miss its light for that long, and we also wouldn't miss its gravity for that long.
Huh.
So the Earth wouldn't start flinging away without the sun holding it for 8.32 minutes as well.
And
So
then
they're tied together. Yeah, it's interesting. And that's another topic.
Yeah, let us know if you want us to dive into those like theoretical questions, those what if you replace the sun with a black hole the same size, what if you took it out, all that sort of stuff. I love those questions, but I often don't get them unless they're from like kids, because the kids are the ones who think big like that a lot of the time, and I love them. I just don't get to answer them much anymore. Anyway, back on topic.
So bearing this time delay in mind, it really helps figure out the size of the universe and what you're seeing when you're looking at the sky. So you're looking at the moon, it's only less than a second and a half for the light to get here. The sun is we don't look at the sun, but it's 8.32 minutes. But the planets we look at all the time. So Mars right now is getting rather close to the Earth. And in Stellarium, you can actually click on an object and get its distance. And so right now it's 3 minutes and 52 seconds for the light to get from Mars to Earth. And it's fun. Because we're getting into this period where Mars is going to be at its closest to the Earth and then start heading away again, you can use Stellarium to monitor how much longer it takes. And not only it's the light that's coming from Mars, but it's also our radio signals to our spacecraft to Mars and back. So right now it's a really efficient time to talk to our spacecraft on Mars, our rovers, because there's only a 4-minute delay in our messages back and forth. But when Mars is on the opposite side of the solar system, it could be another 20 minutes, 30 minutes extra on top of that, which makes it complicated also for human missions to Mars and so on as well. So Mars is just a few minutes away. Venus and Mercury are typically not too many minutes away, light time. Jupiter, when you look at Jupiter, we're seeing Jupiter 45 minutes in the past. That's how long the light has taken. So the sun's light has had to leave the sun, travel 8 minutes to Earth's orbit, and then another 45 to get to Jupiter, bounce off Jupiter, and then come 45 minutes back to your eyes on Earth. So the light has been traveling for more than 90 minutes, but the light just from Jupiter to you is only 45. And that means that when we look at what the Jupiter's moons are doing, they're no longer there right now. We're seeing them where they were 45 minutes ago. So that's why in astronomy apps and planetarium apps, there's usually an option to switch on and off the delay time caused by light time travel. Stellarium,
That's very cool.
It's on by default in Stellarium, but there is a switch in Stellarium that we could show in an advanced session where you could turn that off. Cool. And that means that the Juno spacecraft, which is orbiting Jupiter, it's seeing the moons in a different place than we are 45 minutes later here on Earth. Now, just to take this to the extreme, Pluto is 4.7 hours away. And that's why it took so long to get the data from the New Horizons spacecraft, because it had a fairly relatively weak radio transmitter, a low data rate, and it also had a long delay time. And so when the spacecraft flew past Pluto, when it flew past Arrokoth, which is Ultima Thule, it's been renamed.
It has?
Yeah, it's Arrokoth now.
Okay.
The engineers didn't know whether it went well for almost 5 hours, right? Because they wouldn't know until 5 hours later when the positive radio signal gets back. So all this is kind of a preamble to then talk about the stars. So the nearest star, go ahead.
Wait 1 second, because we have questions. And they're in the vein of big questions, and I think anyway, regardless, one question. So the speed of light and the speed of gravity are the same. Does gravity even have a speed? But as far as I know, yes, they are the same, right? or close
Yes.
to.
Yes.
Yeah.
We don't necessarily, we know that the photon is the carrier of electromagnetic radiation, and that photon has a speed. I guess the graviton would theoretically be the carrier of the gravity field, but we don't understand that all that well. But as far as we know, in addition, that the gravity's action, we know this because we use gravity to navigate our spacecraft through the solar system and so on, and understand how things move and work. That gravity operates at the same speed of propagation that that light does.
Right.
Yeah,
So if you're looking at
that's another
something
big
like,
question.
it's a big question, but if you're looking at something like gravitational waves coming from something orbiting something else, you'll see those in the same number of years light would take to get from that place to
Yeah,
us as well.
like billions of light years away, two black holes merged, that kind of thing.
Yeah.
Yeah.
And that would, yeah. So that, yes, but I do think that field is evolving relatively rapidly. So, anyway, yeah, as far as we know at this point in time, if you're watching this several years ahead, then we may be wrong by then.
Sorry for everybody watching in 20 years that
we got it wrong.
we do the best we can, right?
We do
All
what
right,
we can, what we have. There's
so
one
let's talk
one last
about
question.
one more. Okay,
It's about stars though. It's about stars. And I think the answer is no. Can sun's light be reflected by a star in the night sky, making the star that it's reflecting it more bright than usual? I think the answer to that is no, because the stars are real far away from each other, right?
Well, okay, there's a couple of dimensions to that. That's really cool. So starlight can reflect off other things in space. We'll get to that towards the end of our session for sure. But because massive bodies bend space-time and bend light, you can actually see echoes of starlight that have taken a longer trip to get to Earth. So an object can send light directly to the Earth, and some of its light can get disrupted by a gravitational mass and produce a kind of an echo. And so there have been papers published in the media and in science in the last little while about astronomers predicting an event that they'll be able to observe because they know the delay. They calculated the delay that it had to go through to get here. Yeah, so it's cool. It's again another event.
It's not quite that in that case. It's not quite light reflecting off of other stars, but light being bent by the gravity of other stars.
Yeah.
Okay.
So no, it's like if you shine a light on a light, it doesn't.
It's hard to tell.
Doesn't
like
really
even
do
if,
much for you. If that was the question.
That's more or less it. Yeah.
But you can do, and you can get into really cool things like micro lensing, where a star that's beyond a star gets brightened because the closer star acts like a magnifying glass to make the farther star brighter. Yeah, that's another time. Again.
Okay, now we're done all the hard questions. Back to
send in your requests, everybody.
Yeah.
All right. So when you look up in the sky and the stars that you see in the sky, they are all neighbors of ours in our galaxy. Right? Our galaxy is composed of many, many stars, mutually gravitationally bound into a generally a flat disk shape with kind of a stubby bar core, not a round core, but a kind of an elongated core. Not all galaxies are shaped like that, but ours happens to be what we call a spiral galaxy, a flat disk. And it's about a 20-to-1 ratio between thickness and diameter. And it sort of tapers to the edge. And so all the stars you see in the sky are within the galaxy with us. They're our neighbors. And because we're living inside this three-dimensional object, they can be in any direction above us, below us. Our solar system's embedded within a volume of stars all around us, right? Now, the nearest stars tend to be brighter, right? So the star Sirius, which is now rising late, if I go up into the evening, into the east here and sort of bring up. So right around 3 in the morning, 4 in the morning, there's the star Sirius. That's the brightest star in the night sky. It's actually 8.6 years light years away. So the light has taken 8.6 years. So remember, Jupiter is 45 minutes. Sirius is 8.6 years. So that's how much farther the nearest stars are. So they're incredibly far away, and that's why we just don't hop in a spaceship and go to another star, because
You just can't.
the space is so enormous, right?
Yeah. It's our limiting factor when, expanding, well, other than multiple other things, but it's one of the limiting factors in terms of expanding outside of our solar system.
Let's see if I can find another window. There's another star which is visible in the night sky right now. Let's see if I can bring up 61 Cygni. So we talked about this star a little while ago. This is Bessel star. Remember the person asked the question about Bessel star? This is the one where if I center on this star and I advance every year, the star is drifting through the galaxy.
Right.
It has a high proper motion. So this Bessel star is, let's see, 11.4 light years away. And that's one of the reasons why it drifts across the skies, because we're close enough to detect its motion. The star Altair in the Summer Triangle, it's about 16.7 light years away. So that's the one go back to sort of the evening here. Here we go. So Altair is the bottom of our Summer Triangle. And so you get this general idea that the brighter stars that we notice, Sirius, Altair, they tend to be closer, and that's why we see them more brightly. But then we can also see dimmer stars that are, not as bright, but they're also close because they're just not giving off as much light. So the point I want everybody to take away from this is that the stars it's a completely different realm than the solar system. They're magnitudes and magnitudes farther away than the traffic in our solar system. And there's some cool Wikipedia pages that list which are the nearest stars, which are the brightest stars, and it's kind of fun to go through the list and see how far they are.
There's a song early in the Big Bang Theory, the Proxima Centauri is the nearest star. There is a song about it. I'm not sure how accurate it is though.
Yeah. So yeah, in terms of the closest star, it's the sun. And then after that, it's Proxima Centauri, but we can't see it from Canada. But we did talk about it if you go back a month ago and talk about it, take our Southern Hemisphere tour. I showed it then. And it's only 4 and change light years away. So that means if we send a radio signal and there's somebody there to answer and send signal back, within about 9 years, we'd hear back.
That's not bad.
So that's not bad. Now, so that's the stars in the sky, and it's also the Milky Way. The Milky Way is still our galaxy. It's just that part of the galaxy is farther away, and so the individual stars all sort of seem to be one mass. They're about 30,000 light years away, the Milky Way itself. To go outside the galaxy, then we're talking about other galaxies themselves. And as one of our fall targets, we have this object here, the Andromeda Galaxy. And it's a total different galaxy, completely different galaxy. It's 2.5 million light years away. So the stars in that galaxy have sent out their light as a collective, and that light has taken 2.5 or 2 million years to arrive to your eyes on Earth. It's sort of really awesome when you think about it. I am always amazed. And so cool. Because of that delay, our galaxy, our stars in our galaxy are sending their light towards that galaxy. And it's taking just the same length of time. And so if there are astronomers, stargazers on that galaxy looking back at us, and if they had a telescope that was amazing and big enough to see Earth, it would be the Earth 2.5 million years ago, right? Mm-hmm. Before modern humans roamed the Earth.
It's like time traveling.
It's exactly.
But you can only go backwards.
Yeah.
There's a comment from Larry saying that you can go around and find your birthday star, the one whose light has been traveling as long as you are old, which I think is great. And now I'm going to go do that.
Yeah. If you Google the term birthday star, you can get a list of each star with each distance or each year, and you can find your birthday star. I did mine. I forget what it was, but I won't say.
Cool.
I won't say.
Then you'll
Yeah, it's
reveal
kind of
your
a,
age.
it's a, when you're on Facebook and you want to wish somebody happy birthday, that really ups your game. You can sort of take it to the next level.
Chris with all the life hacks.
Okay, so let's talk a little bit about star charts. Now,
Yes.
there's kind of two things going on here. So let's just bring up the sky as a round circle. So at any given time, we have half the globe of the sky over our heads, from the horizon up to the zenith, which is right overhead. And then there's obviously another half that's hidden by the earth below our feet. And we could represent that on a flat piece of paper or on a computer screen by making one of these circles. And this would be similar to what you'd see in, an astronomy magazine. So this is Sky News. And it's the same idea. And all they've done is they've taken kind of a certain date and a certain time, and they've shown you what stars are above the horizon at that date and time. Now in Sky News, they're trying to cover the sky for about 2 months at a time. So they say that this set of stars will be in the sky on this date at this time, or a month later, but 30 times 4 minutes different, because we talked about the 4 minutes per day idea. Mm-hmm. So you can get the same sky on a different date, but at a different time. And so that's how you can sort of make that sky chart work over a number of weeks, just by adding accounting for that. Now, if you've got the sky chart made for the beginning of September, but here it is in late October, then you can do that math. But basically what you're doing is you're going to shave off some stars that you've now disappeared into the west, and you've got some new ones that have been added in the east. So how does this kind of all work? So just like the globe of the earth has coordinates to let you know where Paris is or where a city is, we generally use latitude and longitude. So we have a reference point of the equator along the prime meridian, which runs through Greenwich, England. That's 0 degrees longitude, 0 degrees latitude. Any distance above north or south is so many degrees, between 0 up to 90 at the North Pole and minus 90 at the South Pole. Or you can go east and west a number of degrees from that prime meridian. And of course, half a circle is 180, so you're all the way around the other side of the earth, and you're opposite the earth from the prime meridian. So the sky, being a globe of stars around us, can operate the same way, but we do it a little differently. So we have the celestial equator. So let me just bring up that, make sure I have my markings set up here that I want. I'm just going to turn off the meridian for a second here. So here we have the celestial equator, which is the yellow line here. And it divides the sky into the north pole and a south pole, right? But so yeah, so we can take the sky at any given time, and what we do is we can assign a coordinate to any object that's in the sky, and using comparable to what we do on Earth. So instead of latitude, we use something called declination. Declination is number of degrees from the equator. It's as if we took the Earth's equator, we painted it across the sky. It's the same equator. And we just measure how many degrees up from the equator that is. And if you point to, if I start at the south here and I measure up to Polaris, you can see it's 90 degrees. Oh, cool. So Polaris being above the North Pole of the Earth would be, the coordinates on Earth of the North Polar is 90 degrees north. So it's 90 degrees north, or you can go south from there as well. But instead of degrees east and west, astronomers like to use the hours of the clock, 24 hours of the clock, because the Earth takes the 24 hours to turn around. And so we use a term called right ascension. And right ascension is basically came from by noting the time that a certain object ascended above the horizon. So it's a fancy name, but it just means the coordinate. And the right ascension is basically 0 to 24 hours around the celestial equator. And the 0 is at the vernal equinox. So the vernal equinox is where the sun is, where the sun crosses the two hula hoops in the spring. And so that's the point in the sky where the 0 right ascension is.
Wow. Okay.
And the reason that it's maybe more helpful than degrees east and west is because you're dealing with time, you can actually get a quick handle on when the object will be over your head, how many hours difference it is from the hour straight overhead, the right ascension overhead versus the right ascension of the object that you're waiting for. And so you can say if it's a 2-hour difference, then you can know that it's going to be overhead in 2 hours.
Cool.
It's actually one of the more complicated things in amateur astronomy. If you buy an equatorial telescope, an equatorial mounted telescope, you'll see that one of the dials has 0 to 24 hours on one of the dials. And that's just the east and west coordinate for the sky.
Oh.
So we've actually got a couple of different ways to talk about where things are in the sky. We can talk about their official coordinates, and they'll always be in that coordinate, or we can talk about where they are with respect to the horizon and the zenith. And so we use the terms altitude, in other words, how many degrees above the horizon is something. And so 0 would be at the horizon, and then 90 would be straight overhead. And then azimuth is the left-right coordinate. So you can have a north azimuth or an east azimuth or a west azimuth and so on. But most star charts will use the declination for north-south and the right ascension for east-west. And if you take a star atlas like this, I don't know if you can see that very well.
Yeah.
So that's Pegasus. You can see I've got there's up-down lines that represent the hours. So each vertical line is an hour in this graph. And then there are east-west lines, and they represent 10 degrees north and south of the sky. Now, sky charts are great. They're a neat way to learn the sky. But the tricky part is that they always show the constellation with north up. And Jenna showed this a while ago. She put up her equatorial grid. So if I face south like this, the grid runs between north and south, right? So if I'm looking at, say, Taurus, or if I'm looking at, say, Pegasus, it's not always going to be upright. So let me just do this. If I do this, bring this up. So when I zoom in on this area around Mars in Pisces, north is actually to the upper left. It's not straight up. And so if you're using a star chart, you've got to figure out where north is and tilt the chart to match it, to really get how it will appear in the sky for you. And so the rule of thumb is that if you're looking east from the northern hemisphere, north is going to be where Polaris is, up to the upper left, and south would be to the lower right. So you sort of have to tilt the star chart a little bit to figure that out. Let's see, anything else? I was just going to mention, and we've talked about this before, that Polaris is a really easy way to navigate the sky to learn where things are. And Polaris is the point above Earth's north pole, and it marks the point in the sky that the Earth rotates around. So all the stars will revolve around Polaris. It's not right on the point. It's about almost a finger's width off. Polaris is always going to be as many degrees above the horizon as your latitude on the Earth.
I find these little things of similar, for some reason, I just have such a hard time connecting latitude in the sky to latitude on Earth. And every once in a while, when something like that happens, where you're like, yeah, I guess, of course that would be right. Because if you were at the North Pole and you were looking straight up, Polaris would be straight up at 90 degrees latitude, and it would be at 90. Anyway, yeah, it's just one of those things that's hard to get your brain to connect it for you sometimes. Yeah.
And when you're at the equator, then Polaris disappears because it's gone down to 0 degrees above the horizon, or maybe hugs the horizon through.
Yeah, you're right at the middle.
Now, you can measure this yourself. we've talked about this before. You can measure the sky using your hand. And if you make a fist and hold it out all the way at arm's length and close one eye, your fist covers about 10 degrees of the sky. So in this case, that would be about, I think these are 10-degree lines. Yeah, 60, 65.
Oh, if you zoom in, there's more of them.
Yeah, these are 10 degrees of sky.
Those are 5 degrees each, those ones.
These ones are 40, 50.
Oh, now they're 10. If you, it depends on how zoomed in you are, yeah.
So 10 degrees of the sky. And that actually works for different size human beings because people with smaller fists also have shorter arms, generally speaking. So I usually used to tell students that their fists might show less sky, but actually I found out recently that it probably still works even for a small child because their arm is shorter, but their fist is smaller. So the geometry still works. Yeah. So your fist covers about 10 degrees of the sky. So if you find out from a star chart or something that your object is so many degrees away, you can sort of estimate the difference. The other one we use a lot is the pinky finger. It's about 1 degree of sky. And of course the moon, the sun and the moon are both a half a degree. So you can always cover the full moon or now don't do it with the sun, but you can cover them with the tip of your pinky finger. Now this does, I think, not quite work with little kids because their fingers are dainty and tiny, but even a small child's pinky finger is generally still fatter than the moon. And then you can do other tricks, like you can measure 25 degrees with your thumb to your index finger, and you can do a palm width, which is about 4 degrees or 6 degrees and things like that. So when I write my skylights every week and I'm giving references to things, I'll say that something is so many finger widths away or something is a palm's width away, and you can measure the sky like that.
It's also nice, even if you're just outside and you know that like if you're trying to describe it to someone and they're beside you, it's even if you don't know what the distance is, if you can see 2 objects that are a certain distance apart, just use your hand to figure out how far apart they are and then say, oh, okay, do this at arm's length, and then you get the right distance. It's
really easy. It's and these days, I don't know if people realize, but we used to use lasers to point into the sky, but we're not allowed to anymore because some people were abusing them and pointing them at aircraft and things like that. Not astronomers, but other people.
The cool thing about the lasers that we use was that they're green, and so they can go through a lot of more of the atmosphere than the red ones, and so they're like lightsabers. You can see exactly where you're pointing. And a few still get to, but you have to apply for permits with Transport Canada.
Yeah, we can use them under certain conditions if
you're far enough away from an airport, and if you're not.
And always the 10-year-old boy will ask me if he can have my laser, and I always have to say no.
Yeah.
That's just a thing with star parties.
It's got no permit.
As soon as I pull it out, oh, can I try that? No.
Nope.
Sorry. Okay. Moving along. Let's talk about star naming, because you're going to see that if you get a star atlas, and that's going to come up a lot. So about 350 stars have proper names. So you can see in Stellarium here, I've got Vega has a proper name, Deneb has a proper name. Those are the only, Altair. And if I zoom in, I can get a few more probably.
Later.
Most of the names that we use for stars in Western astronomy are based on Arabic phrases. Often the translations have been broken telephone. They're not quite right, but you can sort of figure out what they meant to be in the beginning. So Deneb, for example, comes from an Arabic expression for the tail. And Deneb is actually the tail of Cygnus the Swan. But there are other stars that use the word Deneb in them, but they use it in a slightly different way, but it basically means the tail. So that only is about 350 stars. By the way, I was gonna come to this later, but on a dark moonless night away from the city lights, you can see about 3,000 stars in the sky.
That's pretty good.
And then there's another 3,000 under the earth that you can't see. So human eyeballs can see about 6,000 stars under good conditions, really good conditions. But of all those stars, only about 350 have names. And in astronomer, if you want to be a good amateur astronomer, you should learn at least a couple hundred. No, I'm just kidding. But you should
Come on,
try
get
to
it together,
learn.
astronomers.
You should try to learn, it's good to learn a couple of dozen, or if you can, a few dozen of the names.
It's like party tricks when you get to show
It,
people, and it's
yeah, it
also,
really helps a lot. Yeah.
yeah.
Um, so there's that. And then there are a few stars that also have sort of proper names because they're special, like the 61 Cygni star I showed you was the two stars that are moving through space. They're called Bessel star just because the astronomer named Bessel worked on that discovery. But in 1603, an astronomer named Johann Bayer, he created a system where he decided to get organized about the constellations. And he said, so in each constellation, let's just assign a Greek letter to each star. And we'll start at the brightest star, we'll name it Alpha. And then the second star will go Beta, Delta, Gamma, and so on down the list. And so he actually assigned that system to about 1,500 of the stars. But those include the ones with names. So Deneb is also Alpha Cygni, brightest star in Cygni. And what he does is he takes the name of the constellation in Latin and he converts it to the genitive form, the of. So Cygni means of Cygnus, or Lyrae. So there's Lyra and there's Lyrae, which means of Lyra. So Beta Lyrae would be the second star of Lyra. So that covers about 1,500. They didn't account for the fact that some stars get brighter and dimmer. So there were some errors or some rules broken. And also there were typos. So it's not strictly accurate, perfectly accurate, but it generally works that way. And then in 1725, this astronomer in Britain named John Flamsteed, he said, well, you've still not covered enough of the stars. We need to get more organized than even that. And so he decided to set up a system where he was adding a number to the constellation. So instead of going from brightest, he started, let's go in order of right ascension. So he said, let's start, and get this right, increase. So they starts at the smallest right ascension and went to the greatest right ascension, sweeping across the constellations, starting at 1, 2, 3, 4, 5. So you can see that Deneb is 50 in that system. And again, he uses the Cygni, the genitive form of the constellation. So when I showed you 61 Cygni, that was Bessel star, that was the two little stars moving through space. Deneb, even though it's the brightest, it's number 50, counting all the stars in the constellation. If I add the boundary, and if I add I'm going to set this up straight up. So right ascension is increasing left to right. So this one is, oh, I got it the wrong way around. So if I start on this side, that's number 6. And by the time I get here, I'm at 21, then I'm at 37, then I'm at 50, and I can go down here, I can get to 64, and I can get up to 78. So depending on the number you're seeing, and these numbers are often part of your star atlases, then you'll know generally east and west where it should be in the constellation.
Everyone's got different ideas for how to categorize stars.
Well, I'm not going to say much more, but I will say that what about all the other ones beyond, the dimmer ones, the ones you add when you look through a telescope or binoculars. And so there are new catalogs that are designed to catch all those stars. So there's the Hipparchus catalog, there's the Henry Draper catalog, there's the Harvard Revised, the Smithsonian Astrophysical. And so if you have a go-to telescope, a telescope with a computer in it, and you've got the hand controller, you'll often find that stars are being listed with a HIP number or SAO or HD or HR. And those are all from those catalogs, Hipparchus, Henry Draper, and so on. And so you'll see those if you just zoom in Stellarium and keep zooming in. So here we've got the 40, but here we've got, I keep going, there's an HIP, Hipparchus, and so on and so on and so on. So even though it sounds crazy, astronomers basically have a number or a designation for every star that they're likely to look at, right?
And this is the interesting thing is I find this kind of cool because it's kind of like a history of the science of astronomy, where you go from, okay, this is what we know. We know that there are this many stars and here are the names. And then it goes, wait a second, no, actually we're going to sort them by this other thing. We're going to sort them by how bright they are. Oh, wait a second, now we can see more. Okay, so we're going to add in a new thing where we can talk about, oh, now we can see more stars. Okay, let's do another catalog. So it's just that sort of like, at a time, people looked at the stars that were up there and went, that's all there is. And then later on, we looked at them harder and we went, nope, there's more. And so it's neat to see it evolve over time like that, and to see the naming conventions hold that history as well.
Yeah. The the stellar classification system that we've mentioned, that's the letters that we use to describe the star's temperature, basically. So there's O, B, A, F, G, K, M. And O is the hot blue and M is the cool red. Each of those letters has a number with it. So if it's a G4, then it means it's more than G, but less than K, right? It's in between the two. So the more technical you want to get, then the more you have to work to create your system to be more accurate.
And now there's just a quick question about star naming when it comes to double stars, because those of you who joined for Explore the Universe, we talked about double stars last week. How do the naming schemes account for double stars orbiting each other when the star's relative placement is key? So if you're going from like, right, whatever ascension to the other ascension, smallest to biggest, and the two stars orbit each other, how do they name them?
So I'm not 100% sure about the relationship between the stars themselves in motion. We're basically using a system of how they look from Earth at a snapshot in time.
Whenever it was developed, yeah.
So generally speaking, in the Bayer system, they add a number. So epsilon Lyrae, the double would be E1 for the brighter star and E2 for the dimmer star of the two. If you get into the two, I don't remember what Stellarium does here. It doesn't always account for them. I'd have to look at a star atlas to figure that out. But generally, yeah.
I was just going to commend Cicely on her questions on their questions, because they are on point. We've had several really good questions from you, Cicely. So thank you.
Thank you. And it's always good to have a sanity check that if we skip past something quickly and somebody has a great idea, we should talk about that. So thanks, I appreciate that. Yeah, so let's talk about star magnitudes, because this is always a little bit mystical to people. Magnitude is the number that we use to talk about how bright an object looks. And we actually use magnitudes for not just stars, but for planets or for asteroids or for comets or even for galaxies and things like that. And it's basically how bright they appear to be in visible light to us. I talked about the 3,000 stars, horizon to the zenith. If you were out in the prairies on a moonless night with no light pollution, and you wanted to count, you can get about 3,000 stars. One way you can do it is use your fist. So if you bring your fist out and you count how many stars are inside the area covered by your fist, that's 100 square degrees of sky. And I think there's 43,000 something total square degrees of sky in a sphere. And you can just multiply by the 4,300 times the number you get behind your fist, and that should be the number you get in the sky. So it should add up to about 3,000 or 6,000 altogether, but 3,000 at any given time above the horizon. So what we do is we use these numbers to describe how bright things are. And when you use something like Stellarium or a star app, it'll actually report to you how bright it is in magnitude value. All right. Now, to unaided eyes, we can see down to about magnitude 6 away from light pollution. If we're in the suburbs or if we're in a city sky where we have light pollution, then it hides the dimmer objects and just leaves the brighter ones. And so that it limits how many of those stars we can see. And of course, binoculars act to collect the light. All the light coming through the lens of the binoculars is being compressed and sent into your pupils, so you're actually augmenting your ability to see the dim objects. It's magnifying the amount of light that goes into your eye. So if you add binoculars, you can up the number of stars visible in the sky to maybe 2 million. And then a telescope can get you up to maybe 50 million stars. Just by
Wow.
the amount of light. It's like a pyramid. So the number of stars at this brightness are so many. The number of stars at the dimmer below it are many more. And the lower you go, the dimmer you go, the more stars you find.
Wow.
It really increases a lot. So the magnitude number that we talk, that you see written down or you hear about, it's on a logarithmic scale. So it's not linear. So a 2 is not twice as bright as a 1 or anything like that. And in fact, the numbers flipped over. So first thing to notice is that Vega is the 0 point. Vega is the baseline for magnitude. So they call Vega magnitude 0.0. Things that are brighter than Vega are more negative. And again, it's negative because it's a logarithm factor. And things that are dimmer than Vega are more positive numbers. And so a magnitude difference of 1, so 0 to 1, is a difference of 2.5 times brighter. Right? So for example, Sirius has a magnitude of -1 compared to Vega's 0. And that means Sirius is 2.5 times brighter than Vega. So it's sort of a simple rule of thumb. Polaris has a magnitude of about +2. And for each integer you go away from 0, you have to do times 2.5. So it's 2.5 times 2.5. So Polaris is about magnitude 1.95, which is about 6.3 times dimmer than Vega, which is 2.5 times 2.5 roughly. The full moon is magnitude -13 and would be 2.5 to the power of 13 would be the amount brighter than Vega it would be. The sun is -27.
Yeah, it's real bright.
And Jupiter right now is about -2.5. So and Saturn, let me just bring those guys into view here. There we got them. Go back to a couple hours here, get them back into sight. There we go, Jupiter and Saturn. So Jupiter being -2.5 and Saturn being +0.35. So it's a difference of almost 3 on the sort of number line, if you want to put it that way. So that means that Jupiter is about 14 times brighter than Saturn in the sky. So that's sort of how we work with that. Again, you don't need to memorize it or really worry about it. It's just in the back of your mind, you can think that for every difference in one number, it's 2.5 times brighter or 2.5 times dimmer. Now we can use that magnitude value for galaxies and star clusters and things like that, but it's trickier because they're not a point source, they're spread out. And so even though a galaxy can have a relatively healthy magnitude number, it still could be hard to see it because that light is spread out over the sky. It's like, spreading your butter too thin on your toast. So you don't get the buttery taste because you've spread it out over too much. All right. Any questions on that?
Nothing on brightness specifically. There is a question about whether or not the sky is elliptical or spherical, which is a big question. I would say spherical, but it's not that's just our perception of the sky.
Well, if you stand at a point and you can look in any direction, then what you have around you is a sphere.
Right.
But that's different from what is the shape of the universe, if that was the underlying.
I'm not sure.
Yeah.
And then we get into what's the difference between the universe and the observable universe, which we won't get into today because we're on beginner stargazing.
Yeah. All right, so let's talk for a minute about constellations. Again, we're just sort of touching on the various basic things about astronomy. So a constellation, most people understand, it's a picture that has been created by connecting imaginary lines between the bright stars. They usually derive from ancient times. They've often been created from everyday animals or objects, or even from mythology, if it's part of the lore of the culture that is seeing it. And the key there is that early in the history of civilization, different cultures weren't in communication with one another very much. I mean, the people of the Aborigines of Australia weren't talking necessarily, as far as we know, to the people, the Navajo of the States, or the Iroquois of Southern Canada. And so each of those cultures were free to create their own idea of what the stars were showing them, how they were being assembled together. Now, Stellarium by default is showing us what Western astronomy has adopted as the way the constellations are arranged. But as you know, if you watched any of our sessions, you can go into the settings and the star lore, and you can show dozens and dozens of different patterns of the way the stars were put together. And what you'll notice if you do that is that a culture that was based in, say, the Southern Hemisphere couldn't see the northern constellations, so there won't be a constellation for those stars, right? They'll only be using the stars that they would see, they would work from. But basically what we have is a set of constellations. There are, in Western astronomy, we have 88 official constellations, and they have been given a designated boundary. And it's just like the boundary of a country. And it's enforced formally, almost like the formal boundaries between countries. And so if an object is on one side or another of the boundary, it's in that constellation that's been assigned to that constellation. And there are no wars or skirmishes about moving the boundaries around. They were decided by the International Astronomical Union at some point, and they're kind of locked into place. And you will occasionally get stars that are shared. So this star Alpheratz is kind of shared on the boundary between Andromeda and Pegasus. But
If
usually
I recall correctly, for Andromeda needed a head.
Yeah, exactly. But basically everything has got its place in one of the ones. Most of the names that we use for constellations in the Western astronomy are Latin. So Equuleus comes from equus, meaning horse. So this is the little horse. There's Delphinus, the dolphin. Pegasus is from mythology, obviously. Triangulum is Latin for triangle and things like that. Pisces is Latin for fishes. And you can go from there.
Oh, sorry. As a marine biologist, can I throw out that Cetus is Cetus the whale and or sea creature type thing. And that's where the name for cetaceans comes from, cetaceans being aquatic mammals.
Exactly. Yeah. Actually, one of the fun exercises to do with students in a planetarium or using software like this is to get them to identify all the animals, get them to identify all the instruments, especially in the Southern Hemisphere where you've got the octans and the other instruments. Yeah, and one of the neat little things about the sky in this time of year, just below Cygnus and above Aquarius, you've got all these cute little animal constellations. You've got the little horse, the little dolphin, the arrow, and the fox.
Yeah.
So these are four cute little constellations.
Tiny little constellations.
The zodiac constellations are only famous because they happen to be the ones that the sun travels through, right? And there actually are 13. If you look at the way the ecliptic crosses through the boundaries of the constellations, and if you go through the exercise, you can see that there are actually 13 that it touches or passes through. But the mystics of old didn't like the number 13. They liked the number 12 better. So they decided to skip or forget the constellation of Ophiuchus when they created the zodiac. But basically the zodiac is a ring around the sky that sort of encompasses the ecliptic, and each one is roughly a month's worth of travel for the sun. So you'll have heard many of those constellations because they're always where the sun, the moon, and the planets are going to be sitting inside. So you'll hear about Saturn being in Sagittarius or Mars being in Pisces or so on. And that's so that they get a lot of press because there's a lot of conjunctions and things that are associated with those particular constellations because of the way the solar system passes through them. But other than that, they're nothing, they wouldn't be special in it for any other reason.
And along with that, the constellations are also all made up anyway, so.
Yeah. In ancient China, they had 212 constellations. And in fact, many of the bigger ones were broken down into little pieces and they saw other things. So, and students are welcome, or you're welcome to go out and invent your own, which is what an asterism is. So an asterism is an informal pattern. So the IAU has no ruling here. You can go ahead and make up your own constellation, your own star pattern, and call it an asterism. The Big Dipper is an asterism because it's just a piece of the bigger Ursa Major. Or the Summer Triangle is an asterism. And again, we can bring up the asterism pictures here. Summer Triangle steals from 3 different constellations to make a triangle. The Winter Hexagon, which is going to be in our sky within another month or 2, you can see it here coming up. Here's the big Winter Hexagon, or Winter Football. It's usually in the sky around the Super Bowl time. So it starts with Sirius, Rigel, Aldebaran, Capella, Castor Pollux, and Procyon, this giant oval. And it's informal. It's just fun. It's a way to have fun with astronomy. All right. So let's wrap up by talking a little bit about deep sky and what that's all about, and then suggesting some targets for people to take a look at this fall. So a deep sky target, when you hear astronomers talk about deep sky, they're talking about anything that's worth looking at that isn't part of the solar system and that isn't a single star. So the base starts at double stars. So 1 star doesn't count, but 2 stars counts. So you can have a double star, could be considered a deep sky object, or multiple stars. Then you can also have star clusters, you can have nebulas, and then you can have galaxies. And of course, star clusters, nebulas, galaxies, those are like the primo, cream of the crop.
The Cadillacs of deep sky.
Yeah, the best of the best. So star clusters are just collections of stars that are near to one another in the sky. They've often been formed together. They've often are the same, born of the same molecular gas cloud, and they're now just sort of drifting through space together. One of the cool ones to look at this time of the year in the evening is to face the northeast and focus on this bright star Murphak, which is in Perseus, and you can tell it's below the W of Cassiopeia. So find the W of Cassiopeia and then look for a bright star below that. And if you use your binoculars on Murphak, there's this really amazing patch of bright stars that are surrounding it. And that's called the Alpha Persei moving group. Alpha Persei is Murphak, right? It's using that Bayer system, Alpha Persei. And so it's just basically stellar siblings that were born from the same cloud, and then they're now sort of traveling through space as a group, and they happen to be around Murphak. I don't think Murphak is part of them. Let's see, 558. Might be. I forget. I haven't looked it up, but that's a neat one. That's a what we will call an open star cluster. So an open cluster are association of stars. They can be quite big in the sky if they're near to us, and they can be as small and compact if they're farther away. Another neat one is up in Cassiopeia. Let's see if I can find NGC 457. I think it's this one. Yeah, this is called, let me just get this.
Hey, I recognize that one.
Yeah, this is the owl cluster. I'll do it this way. NGC 457. There we go. The dragonfly cluster or owl cluster. It's an open cluster again. This one happens to form in a whimsical shape. It looks like an owl. He's upside down. I can make him right side up if I do kind of flip him like this. You can see the 2 eyes, then the body is the stars. He's got a couple stars for feet, and then he's got wings that come up left and right. So that's an open star cluster, and those are really, really great ones to look at. Some of them are naked eye, some of them are great in binoculars. And this one is sort of sitting, if you count the W of Cassiopeia, so 1, 2 stars, and then sort of go to the right, you can find it with binoculars, is that one. Then you can get globular clusters. So globular clusters are also made of stars, but these ones are many, many more stars. They're more compact, they're bound by gravity, and they tend to be spheres. They're balls of stars. Let's see, the late summer, we can still see M13. So let's get down to M13. Let me just bring on the deep sky objects on here. There we go. So M13 is a globular star cluster. And just hide the symbol here.
Ooh.
It's hundreds of thousands, maybe even a million in some cases, stars. And it looks like salt on a black velvet tablecloth. You can see them in naked eye from the cottage if the sky is nice and dark. And you can certainly pick them up in binoculars or telescopes. They're really, really neat objects. So those are sort of two different types of star clusters. If you look at the constellation of Taurus, the bull has a V-shaped face. That V shape of stars, that's a star cluster. It's one of the closest ones to the Earth, so it's big, forms almost a whole constellation. So then that star cluster. The next thing are nebulas. So nebulas are the gas that the galaxy is made of. And again, these are all part of our Milky Way so far. They're within our Milky Way. So nebulas are made of gas, primarily hydrogen gas. And if you can get the hydrogen gas to glow by putting radiation into it, then the hydrogen will emit in a reddish or pinkish light. And one of the coolest ones to see is up here near Deneb. And you can see there's a little sort of a pink patch here. And this is called the North American Nebula. And it's hydrogen gas that's glowing through the radiation of the stars in the vicinity. So we call that an emission nebula. And these can be really big in the sky. This object, this North American Nebula is actually, I mean, this whole set is about 3 degrees. That's 6 times as wide as the moon. The North America part is smaller. It's about 2 moons. There's a second sort of a separate lobe to it. This is called the pelican. I don't know if you can see that there's a pelican's beak, his back of his head, and then his body is curved down here. It's all one cloud of gas, but there's dust that's divided it. But that's in the sky, it would span a couple of finger widths. And you can find it sort of down near Deneb, just to the lower left of Deneb in late evening around now. Okay, so that's called an emission nebula. These ones are good for bigger telescopes. They're good for binoculars if you're at the cottage because you can pick them up. And if you have, because they give off a certain wavelength of light of the glowing hydrogen, they're good for, they're good objects to use filters on, special filters made for nebulas that you can make them brighter. The most famous one is the one we all wait for. Down here in Orion. And that's the Great Orion Nebula in his sword. And you can see the pink, the glowing pink from the hydrogen gas. But what the Orion Nebula has going for it is something extra special, and that's called a reflection nebula. So the reflection nebula is made of dust instead of gas. And it's actually, when stars' light scatters off dust, it scatters with a blue light. It's the same thing that makes the sky blue on Earth. And that scattered light gives you a blue sort of halo around some of the bright stars. And those are called reflection nebulas. And you can see that real blue just above the Orion Nebula. You need a big telescope to be able to see the colors. Sometimes you can, but certainly the photographs pick them up, the colors. But the other cluster, the Pleiades, that people know as the Seven Sisters. Where's the Pleiades? Here's the Pleiades. So the Pleiades are famous for having that blue halo around them because that's the reflection nebula. That's the dust that's giving that halo around them. Then you can have supernova remnants. So supernovas are gas that have been exploded from a star that died, and they're generally sort of a round shape, a spherical shape. There's a couple of different ones in the sky. One is the Crab Nebula, which is hard to see for amateurs, but it's actually, I'll just bring it up here to show you. So if you look at Taurus and the two stars that make his horns, just above his lower horn is the Crab Nebula. So that's a supernova that was first detected in 1054 when a star was exploded. It was so bright you could see it in the daytime. But the really cool one that I showed Jenna how to find the other day, ago, it's back here in Cygnus. Let's go back to the evening time here.
This was, while you're finding that, I'll just plug our Discord channel, because we have a Discord server, which is where we were hanging out and chatting on the voice chat while observing, and it was great. And Chris was very helpful. And at some point we'll do a similar thing, except instead of Chris doing all the grunt work and telling me what to find, I'll actually sit down and help other people.
So if you find Cygnus in the sky, look for Deneb, look for the star Saturn, which is the heart of the swan, and then drop down the wing. So go to the first sort of joint in the wing, second joint in the wing, and in between them, you want to jog a bit to the right, and you can look for a naked eye star called, let's see if I can pick up the star, 52 Cygni, again, using that 52 system that Flamsteed mentioned. And this is the remnants of a supernova that exploded many thousands of years ago. I'm not sure the date right now, but it's actually already starting to dissipate. So it's kind of a ragged, broken into pieces. And so if you put your telescope on 52 Cygni on a dark sky, and it's a good size aperture telescope, you can see the light streak of the nebula passing right through the star. The star is not related to the supernova remnant. They just happen by luck to give you this really cool signpost, a way of finding the supernova remnant easily. So that's called the Veil Nebula. There's a sort of an east half and a west half. Then there's planetary nebulas. So here we have emission nebulas, reflection nebulas, supernova remnants, and planetary nebulas. Planetary nebulas are stars like our sun that have exploded. And the most famous one of that is in Lyra, and that's the Ring Nebula. And the exploded star just produces a little disk of gas that glows with a central star. That's the white dwarf star in the middle. All right, coming to the end here. So the last sort of stop in our deep sky tour would be galaxies. So unlike all of these other objects, the galaxies are not inside our Milky Way. They're millions of light years away. Galaxies can be 2 million light years away, like the Andromeda one, or they can be 40, 50, 80, 100 light years away. You can still see them with amateur telescopes if you've got a nice dark site to look from, and go from there. So hopefully that's given you some basics, some inspired you to look at some objects. The way to find the Andromeda galaxy, right now it's in the evening, it's in the east. It's about, let's see, about halfway up the sky. After dark, around 10:30 or almost 11 o'clock, look for the square of Pegasus. You can find that star Alpheratz, which is shared by Andromeda and Pegasus. And you can drop down 1 star, 2 stars, and then go up, and you can find it. It's about 6 full moons across and about 2 full moons high.
It's huge. It's unbelievable.
And it's one of the farthest away things that a human eyeball can see without help. 2.5 million light years. There's another one down here called the Triangulum Galaxy, which is a little bit farther, and some people have been able to see it if their sky is really, really black. And
like naked eye with no binoculars?
Quite big in binoculars. Yeah, you can see them in binoculars.
Cool.
It's just so the Triangulum Galaxy is quite face on to us. So when galaxies are on their edge, all their light is concentrated into a strip and it's brighter. When the galaxies are face on, all that light is spread on the toast like the butter, not enough butter on your toast, and it makes it harder to see it. But they're fun to look at.
Cool.
So there you go. There's your whirlwind.
That's amazing. Those are some excellent targets. And we will actually, so Alpha Persei cluster thing. That's one of our targets for Explore the Universe this fall as well. So if you're looking for more targets, there's also, there's another show on the RASC channel called Explore the Universe, where we go through one of our observing certificates and show you how to find the different targets in that. So that one's in there as well. And I had a hard time describing that one. So thank you for adding it in here.
No problem.
There's a question from, hold on, Cicely, again, thank you, Cicely, asking, how do we beginners know if we're looking at a star cluster or just a bunch of stars that appear close together?
Well, if they appear close together, you probably found a cluster. No, it's not really magical. And what you can do is you can grab your astronomy app or Stellarium, like note where it was compared to the brighter stars around it, and maybe go and look up and see if there's an object that was there. I mean, if you grab a star atlas like this, all the little symbols on here represent the various clusters, and they use different types of symbols for the different objects. But chances are you probably did see a star cluster. The other thing is that most of the star clusters are preferentially near the Milky Way, because that's where most of the stuff in the galaxy is. And so if you're looking anywhere near the Milky Way, then you probably found one, and it's probably got a number or a name. And you can see in Stellarium, we've got all kinds of weird, whimsical names for these clusters and nebulas. So
yeah, I would also say that, I mean, generally speaking, so you'll occasionally see, we've talked about double stars in the past where one star is close, one star is far. They just look like they're really close to each other from our perspective. But the odds of that happening with like 30 or 40 stars are really low. So if you see that group of stars, and also it helps if they're all kind of similar brightness or like color-ish. Usually they're in the same kind of cloud.
Yeah, usually if they're siblings, they have the same composition. So they basically have the same size and temperature and so on.
So that helps a little too, yeah.
Once in a while you get a foreground star that's like doesn't belong with the rest. And so it makes it fun. It makes it really cool to see this sort of weird, golden star and then amongst all these other blue stars.
There's a couple more questions and then we're going to wrap up because I know we are running a little on the late side. Are there any filters that you can add to binoculars to be able to see nebulae better?
Yes. So the best filters for nebulas would include oxygen 3 filter is one term. High contrast or nebula filter, you can Google and shop for. Most of those filters are the size designed to fit on telescope eyepieces, but you can, if you're willing to spend the money, you can buy them that are the size to fit on your particular binoculars. Most manufacturers sell a range of sizes so that you could probably find them. It's not something we normally do, but you could do it probably.
Yeah, I think if you're going to go for binoculars, my bigger recommendation would be just get somewhere darker. And darker is better in terms of being able to see nebulae and stuff like that.
Yeah.
This is a great question, although we've gone over it before, so I'll just be maybe really quick in answering it. How was Polaris detected and therefore became what we term the North Star, and that it should happen to align north for us? So it's actually an optical illusion. Polaris is only the North Star because it appears to be above the North Pole, essentially, but our North Pole, South Pole axis actually does wobble over time. And so the North Pole is the Polaris is only the North Star right now, but in 13,000 years, we'll have a very different North Star in a couple, and even as we go forward in time, about every 50 years or so, they have to redo star charts because the sky has moved enough and we've wobbled enough that it's a little bit different. So that's the path that our North Pole takes. Thank you, Chris, for throwing that up.
Yeah. So two cool things. So this Sunday, when I published my skylights, I wrote a story about Cepheus. I'd never done a deep dive tour of Cepheus before. So if you go to astrogeo.ca and you can look for the story about Cepheus, and I called him the king of the North Pole because he's the king in mythology. But each of these stars will take a turn being the pole star in the future because they sit near this circle. This is the precession circle that Earth's axis will trace out over many, many years. And each planet in our solar system has a North Pole on its rotation axis, and Earth has a 23-degree tilt, and so does Mars is similar, and Jupiter's is similar. Sorry, Saturn's is similar. So they have stars that act as their North Pole stars, but the sun and most of the planets have their North Poles near Draco, inside Draco, sort of inside the center of the circle. So that's a cool fact. And then there's, you know, planets that have been tipped over that have a completely different, pointed a completely different direction.
Yeah, because Uranus is totally on its side. Okay, last question, and this is just about Mars, and I wanted to also add that we are going to have a session specifically about Mars on the day that it is brightest and highest in the sky, which is October 6th. So join us for that. But this question is that George thought that they could make out some white patches on Mars this morning. Are the polar caps visible right now, or was it just an optical aberration?
No, you definitely can see it. If you get almost any size telescope now, should be able to see a bright patch or a bright speck near one edge of Mars. And depending on your telescope, it might flip it upside down. Stellarium's not showing it very well, unfortunately, but you can see there's a little brightening here. That's the south polar cap of Mars. So Mars is just had its northern winter begin. So that means its south pole is tipped towards Earth a little more. So you should be able to see the bright patch of the south polar cap. And don't wait. Start looking at Mars. It's already great to look at already. So
yes, you'll be ahead of the media as well, because the media is not going to start talking about it until like October. So
you can spend the next month looking at Mars, and every night, because Mars rotates at a different rate than Earth, then every night you'll see a little different piece of Mars.
Yeah, watch it over time. That helps.
Go back and watch 2 weeks ago. We talked about this more.
Yeah. All right. Thank you everybody for joining. There was one question that I saw in the YouTube chat as well. I don't know if you want to answer it right now, Chris, which is recommendations for books involving gravitons and gravity and that sort of stuff. I gave my suggestion of The Universe in Your Hand by Christophe Galfard, which I think is a really good book. Do you have any off the top of your head that you'd recommend?
Not off the top of my head. We can maybe.
We'll put together a list.
Yeah.
Yeah, we'll put together a list and we'll put it in the YouTube description once we come up with it. So maybe it'll be there by the time that you watch this. All right, perfect. Thanks everyone for joining. Our next session is going to be in 2 weeks, and we are going to be talking about, oh no, I closed the window.
Telescopes.
Telescopes. Yeah, we're answering all of your telescope questions. We've had questions about what eyepiece do I use to see this? How come I still can't see it? All that sort of stuff. We're going to go through in depth how to set up your telescope and what you have to think about and all that sort of stuff. So we're diving into telescopes. Bring your telescopes and your questions on Tuesday in 2 weeks. So that'll be later in September, and we will get answering them then.
And I won't have as much material, so it'll be much more interactive. So we'll take your questions and talk more about what your issues are.
We'll also both have our own telescopes set up, and we'll have them right there so we can show you all the different stuff that way.
Fantastic.
We'll see you then. We have a request for setting circles. Help me remember that, Chris. We'll talk to you guys soon, and we'll see you in 2 weeks. Happy observing, and then go and enjoy Mars if you can.
Keep looking up.
Keep looking up, clear skies.